What specific problem does your proposed full-stack measurement approach aim to solve in the context of AI environmental impacts? And why is it important to establish a comprehensive measurement boundary?
The proposed full-stack measurement approach aims to solve the problem of inconsistent and often narrow estimates of energy consumption, emissions, and water usage associated with AI model serving, which can vary significantly due to differing methodologies and measurement boundaries. This inconsistency leads to a lack of reliable data, making it difficult to understand the true environmental impact of AI applications. Establishing a comprehensive measurement boundary is crucial because it ensures that all material energy sources, including active AI accelerators, idle machine energy, and data center overhead, are accounted for, providing a more accurate representation of the environmental costs. By including these factors, the approach not only enhances transparency, but also incentivizes efficiency improvements across the entire AI serving stack. Ultimately, this comprehensive framework is essential for driving meaningful reductions in the environmental footprint of AI technologies.
How does the proposed methodology for measuring energy consumption work? Illustrate it step by step, including how energy measurements are collected and what constitutes the measurement boundary.
The proposed methodology for measuring energy consumption in serving AI models involves a comprehensive approach that includes several key steps. First, it establishes a measurement boundary that encompasses all energy-consuming activities associated with large language model (LLM) serving, specifically focusing on material energy sources under Google's operational control. This includes active AI accelerator energy, active CPU and DRAM energy, idle machine energy, and overhead energy captured by the Power Usage Effectiveness (PUE) metric. Next, energy measurements are collected using internal telemetry across Google's AI serving fleet, where power supply unit (PSU) energy consumption is tracked for both the host and AI accelerators during inference runtime. The methodology calculates total energy consumption by measuring the power consumed during active and idle states, factoring in the total time allocated to each job and the portion of that time spent idle. Finally, the energy components are divided by the total user prompt count to derive energy consumption per prompt, ensuring that the measurements reflect actual operational conditions rather than idealized benchmarks.
Can you provide a simple yet illustrative example of how your proposed method calculates energy consumption per prompt using the comprehensive approach? Walk through the steps with sample data.
To calculate energy consumption per prompt using the comprehensive approach, we follow a structured methodology. First, we identify the total energy consumption components for an AI model serving a prompt, which includes active AI accelerator energy, active CPU and DRAM energy, idle machine energy, and overhead energy. For example, let's assume we have the following sample data. Active AI accelerator energy is 0. 14 watt-hours, active CPU and DRAM energy is 0. 06 Wh, idle machine energy is 0. 02 Wh, and overhead energy is 0.02 watt-hours. Next, we sum these components to get the total energy consumption per prompt. 0. 14 watt-hours plus 0.06 watt-hours plus 0.02 watt-hours plus 0.02 watt-hours equals 0.24 watt-hours. Then we measure the total number of user prompts served during the measurement period, say 1,000 prompts. Finally, we divide the total energy consumption, 0.24 watt-hours, by the total number of prompts, 1,000, to find the energy consumption per prompt, which in this case would be 0.24 watt-hours prompt. This comprehensive method ensures that all relevant energy sources are accounted for, providing a more accurate representation of the environmental impact of serving AI prompts.
What are the theoretical or practical benefits of using your method over existing estimation and empirical measurement approaches for AI inference?
The proposed comprehensive measurement methodology offers significant advantages over existing estimation and empirical measurement approaches for AI inference. Firstly, it establishes a clear measurement boundary that includes all material energy sources, such as active AI accelerators, CPU and DRAM energy, idle machine energy, and overhead energy, which are often overlooked in narrower methodologies. This results in a more accurate representation of energy consumption, as demonstrated by the comprehensive approach revealing a total energy consumption that is 2.4 times greater than estimates from existing methods. Secondly, the methodology employs direct measurements from Google's AI serving fleet, ensuring that the metrics reflect real-world operational conditions rather than relying on potentially flawed assumptions, which can lead to significant variability in reported figures. Lastly, by focusing on median values rather than averages, the methodology provides a more robust and representative metric of typical user impact, thereby facilitating better comparisons and incentivizing efficiency improvements across the entire serving stack.
How was the comprehensive methodology validated, and what datasets or benchmarks were used to demonstrate its effectiveness?
The comprehensive methodology was validated by applying it to Google's Gemini Apps product, where it measured critical environmental metrics such as energy consumption, emissions, and water usage per prompt. This approach utilized internal telemetry data from Google's AI serving fleet, allowing for direct measurements of energy consumption across various components, including active AI accelerators and host CPUs. The results were compared against existing methodologies, which often had narrower measurement boundaries, revealing that the comprehensive approach yielded a total energy consumption figure that was 2.4 times greater than those from existing estimates. Additionally, the methodology's effectiveness was demonstrated through a significant reduction in emissions per median prompt, achieving a 44x reduction over a year, which was attributed to various optimizations in model architecture and operational efficiencies. This validation underscores the importance of a full-stack measurement framework in accurately capturing the environmental impact of AI serving.
What limitations or drawbacks have you identified in your proposed method, particularly regarding the measurement boundary and data collection processes?
In our proposed methodology, one significant limitation is the measurement boundary, which excludes external networking energy consumption and end-user device energy, as we lack operational control over these factors. This exclusion may lead to an underestimation of the total environmental impact associated with serving AI prompts. Additionally, while our comprehensive approach aims to capture all material energy sources, it relies on internal telemetry, which may not account for variations in energy consumption across different operational contexts or hardware configurations. Furthermore, the methodology's reliance on historical average emissions factors for carbon calculations may not reflect real-time fluctuations in grid emissions, potentially skewing emissions metrics. Lastly, the complexity of accurately measuring idle machine energy and overhead energy in a dynamic production environment poses challenges in ensuring precise data collection and analysis.